Just looking at the stress matrix. How do you decide how something's going to deform? As in one where
okay.
You have a stress tensor, and I was like, how's this object going to?
Okay, so 13. So it starts out by giving you a stress tensor,
Yeah.
And one of the steps is to calculate the strain, right? That's the easiest way to, what's given stress. Sketch the deformations that would occur. Okay. Well, I think it's probably true that the easiest way to do it is to just calculate the strain. But in this case, you can sort of think it through too. So yeah. Well, let me give you sort of a systematic way to think through it in this case, sort of this simple example. So we got 5, 10, 0, 10, negative 5, 0, 0, 0, 0. And this is megapascals. What's going to happen due to that XX? You know, the key is that it's positive, not that it's 5. That is, so along the x-axis, that puts it into tension, right? It's stretching along the x-axis. Is it going to do anything else? Yes. So the Poisson's effect says it's going to compress along y and z. Okay, so that's what we have so far based on that one. And then we have the second one that says we also have a y stress equal to negative 5. Again, the key is the negative, not the magnitude. And that, due to that negative stress, we're going to have stretching along the y-axis, compression along the y-axis, because that's negative. And the Poisson's effect, what does that require? Stretching x and z. And then the shear stress in the xy position is positive 10. What? The matrix. And so what do we know is going to happen with that positive xy shear stress? Yeah, we know that that's going to lead to a positive xy shear strain. And a positive xy shear strain means the positive x, the angle between the positive x face and the positive y face is going to get more acute. Okay. Okay, so based on all this, if I say that this is the original shape of an element, what's going to happen along the x-axis? It's going to stretch due to this one. It's also going to stretch due to this one. So the new length is going to be stretched, right? Who's with me? And now let's think about y. The y-axis, due to the xx stress, it's going to compress. Due to the yy stress, it's also going to compress. So the length along the y-axis is going to get smaller. So, whoops, I shouldn't draw these yet. Because the angles are going to change. I'll draw. So here's what we know so far. Due to the normal stresses, we're going to be at that blue position. And now we know that the angle between the positive x face on the right and the positive y face on top is going to get more acute. So the final answer is something like that. Yep. Yeah, positive shear strain means the angle between those positive faces gets more acute. Okay, because so if this is your if this is the cube, right? Now think about what face the positive x-axis would be an alien for. Okay, so that means that this is the positive x face. And then which one for the y-axis? That would be this one. So that's the positive y face. And so then the angle that we're talking about is the angle between those two faces. And so that gets more acute. Yeah. Any other questions about that one? And so one thing that I conveniently drew this in the XY plane, I ignored what's happening in the Z direction. The Z direction is the only one that the two different normal stresses give inconsistent information for. The Z-axis, along the Z-axis, the XX stress is going to cause compression, and the YY stress is going to cause stretching. It turns out that since these both have magnitudes of 5, those are going to completely offset each other, so you'll have no stretching or compression in the Z direction. The easiest way to do this problem is, I think it's a good exercise to just think through this kind of thing, to remind yourself what the physical meanings are of all this stuff. But the easiest way to do it is just choose some random values of Young's modulus and Poisson's ratio, calculate the strain, and then and then use the strain to tell you what the deformations are going to be. There's none. That's right. We know that there's no XZ or YZ shear strain because there's no XZ or YZ shear stress, and there's and the reason there's no normal strain in the Z direction is because they offset each other. That's harder to see, but if you did the calculation, you'd see it. Any other homework questions? Thanks. All right, so here's where we are now. We know everything that we need to know for the whole class about the relationship between stress and strain. So the relationship between stress and strain is done. If you're given a complete set of strains or a complete set of stresses, you can find the other ones, the ones that you're not given, based on the compliance or the stiffness matrix. From any complete list of strains or any complete list of stresses, you can calculate all the principal stresses, you can calculate the maximum shear, and that's all the stuff that you're going to do. So now, what we haven't done a single time yet is we haven't connected this idea of stress, actual physical loads. And so mainly the rest of the class, we're going to spend talking about how to calculate stresses due to external loading. Okay? We did it in terms of the traction a little bit, but we figured out some ways to put restrictions on the tractions or the stresses or whatever. And we're actually not going to really use that approach. That's something that you use with more advanced stuff like this. But what we're going to see is now if you have a beam like this and it has loads like this and it's connected to the wall like this, what can we say about the stress an inch from the top of the beam and a foot from the end? That's the stuff we're going to be able to do now. Yeah, so now we're going to take the next step from those internal loads from statics and calculate the stresses, which gives you a little more specific information. Okay, so now for most of the class, we're going to learn how to calculate the stress at individual points given external loads. So we're going to learn about that in a few different categories, a few different ways of thinking of loads. The first one and the easiest one to deal with is if you have an object that's loaded according to the rules of stress elements, of those stress cubes. So the easiest case, that's not how you spell easiest. Easiest case. Objects loaded like a big stress element. Okay, so let me give you some examples of ones that fall into this category and some that don't. anything in uniaxial tension or compression. That works because stress element can be loaded like this. Yeah, I mean, it doesn't matter. You know, you could choose whatever coordinate system. But basically, you're going to look at this thing and say, if you remolded that into the shape of a cube, would it be following the rules that are required for stress? Okay? The rules for the stress tensor say you have to have equal and opposite forces on the two sides. So this one's good. So this one, yes. What about this one? Where you have a tension here, and that's counteracted by you know, forces on the two sides like this of T over 2. Well, yeah, if you imagine that being a stress cube, that would look like this, and this, and this, yeah, that obscured side. And so this one doesn't fit into this category. It's not like you can't do that to an object. It's just you can't calculate the stresses the way I'm telling you right now for if you did this to an object. No, you can do, so here's an example with shear that would be fine. So what if you had a rectangular element like this, and you had it loaded this way, and this way, and this way, and this way, and then, you know, with the corresponding ones down the sides, or I guess up that side and then over along the bottom. That'll work as long as the loads put it in equilibrium, because that follows the rules that say you have to have matching shear there, there, and then this. Yeah. So that's what we're looking at right now, and a lot of the most important case is going to be this case where we just have tension or compression on one side of like a long whatever you call it, whatchamacallit, long thing. R. Forces?
As in,
internal loads?
on the stress cube, it's assumed that that's at the center of X space. Is it also assumed that this is at the center of X space?
Which one? Yes.
As in, on the stress cube,
Oh,
you have,
and this is that stress cube representing the middle of that?
as in the stress cube.
Yep.
An XX, YY, or ZZ element comes directly out of the middle of the face.
Yes.
Where the forces are on the actual object matter for this? If you get what I'm saying.
No, I guess I don't.
As in, if you have, say, this board,
Yeah.
is the force here going to be the same as?
That's a good question. Okay, that's an important question, and I'm going to talk about that in just a second. Yep. So actually, I'm going to talk about that right now. One key idea. We know that that's supposed to be straight. We know that if this is a distributed load, a uniform distributed load, then this is an element that's loaded. This member is loaded like a stress element. This member with uniform distributed loads at the ends qualifies. What about this? So let's say we have that same object, and instead of a uniform distributed load, we have a single point force like that, and a single point force like that. Okay. So yeah, so let's think about what would happen if you really loaded, if you could somehow apply a force just to that point and to that point, or a localized force just around a small region there, instead of applying it evenly over the whole face. Okay. I mean, if this was made out of silly putty, what would it do? You know that it would stretch this little piece out, but not the whole face. It would stretch this little piece out here. And so steel or whatever would do the same thing to some extent. It wouldn't be as visible. But applying to loads like this would cause big stresses where the force is applied, big deformations where the force is applied, and different things over here. And if we can't, so if we're limited to only dealing with loading like this with uniform distributed loads, like the stress cube itself, that's a big problem, because there aren't many things like that. Is everyone with me on what I'm talking about? Mhm. Well, if you did this to a steel bar, right near that loading, yeah, there would be shear stresses and normal stresses that would be hard to predict. You couldn't predict it with the approaches that we're going to be talking about in this class. And what we'd really like is for this to be in some way equivalent to the case when you have the uniform loading. And it turns out that so saved by what's called Saint Venant's principle. Saint, V-E-N-A-N-T principle. This is the other kind of principle, not like principal stresses. I don't know anything about Saint Venant, but I would guess so. I mean, I know. False advertising otherwise. And Saint Venant's principle says the behavior of two equipolant systems will be the same if you're looking far enough away from the loads. Okay, so the sort of rule of thumb distance is if you get once you get okay, this, let D be the longest dimension of the loaded face. Then any force can be treated as a uniform distributed load if you're at least the distance d from the loaded face. So here's a figure that I think will explain this somewhat. So if you have a prismatic rectangular bar with point forces applied at the two ends, say that's 50,000 newtons, 50,000 newtons. And you're comparing that to an identical bar. This time, those 50,000 Newton forces are uniform distributed loads. Yeah, over the whole face, yep. Then, at the ends, where those loads are applied, you can't trust the approximation. You can't assume, so let me draw the, or the results do not match for these two. Okay. So if you're trying to analyze this by assuming that this is a uniform distributed load over that face, okay, you're going to get useless results close to the loaded face, okay? But for the rest of it, all the rest of this, those results are going to match. Okay, so if all we want to do is figure out approximations for the stresses far away from the two ends, then we're in business. We can think of this as being loaded like a stress tensor. We have to be really careful and actually just throw out our results near the loaded faces, because our assumption that it's loaded like this are not going to give us anything useful when it's loaded like that.
So basically, just because this one acting on one point, but the other is acting for the whole.
Yes, that's why, yeah. There are local stresses that come from how that load is applied. And so if you're close enough to the load, they're different. But if you go far enough away from the load, and you don't have to go that far, like imagine this being an I-beam or something. The place where these I-beams are loaded at the end is often pretty small compared to the length of the beam. And so then you're happy to trust the results for the majority of the beam and just throw out the results that you get
Oh,
at the ends.
and even the value for both, like, the don't match, like the don't match area, the value would be all up or really, like.
It depends how the load is applied. And it can be really a big difference or not that much difference. But for this class, the take-home message is whenever we're dealing with beams, you're probably going to throw out the results at the ends. You can't make assumptions about what the stresses are going to be at the ends, but you can in the middle of the beams. Okay, so we're going to start out by dealing with, okay, so the most important category is not uniform, uniaxial tension or compression in bars. And one place where that occurs is in trusses. And so those are the problems that we're going to see these in for now. So like, for example, if you have a truss like this with a 10,000 Newton load on top, so in this case, this is a structure. If you have a structure where every member is a two-force member, then every member is in uniaxial tension or compression. Okay, so what's required for a member to be a two-force member? We talked about that in statics a little bit. Yeah, that's so. What we so the rule is that for members in a structure to be a two-force member, you can only have force vectors applied at two places. So like this one over here has a force vector applied at the pin and a force vector applied at the top. You know, it actually has a force vector applied by this one and a 10,000 Newton force, but since they're in the same place, that ends up adding into a single vector. If you included the weight of the members, there would be a third force acting at the middle, and then it wouldn't be a two-force member, and you can't use this simplification. But a lot of times you'll make that simplification because if this thing is built to support huge loads, you know, say it's part of a supporting structure, then the forces applied to it are going to be really big compared to the weights of the individual members. And so you can throw that out without messing up the accuracy very much. You know?
So only one force applied to one of the structures. So this was someone.
So, well, each one of these has, so this one has a force vector applied here and a force vector applied there. And the other one has one there and one there. So they're both two force members. Okay, so let's let's say, if each member has a length of 1 meter, and a cross-sectional area of, let's say, 0.5 times 10 to the minus 4 meters. What are the stress tensors for each member? The way that we emphasized doing it in statics was to isolate, each of those two rigid bodies, associate the pin with the lowest numbered member at each joint, go through all that, and that'll work fine. If you have trusses, you can use a simplified approach where you isolate the pins and sort of think of all of the members as cables that can support tension or compression. So let's talk about that approach. Yeah, you can do it that way, yeah. There's a faster way for trusses. So let me label all these. Let's call this joint A, B, and C. Oh, and this is supposed to be an equilateral triangle, so let's say that's 60 degrees, 60 degrees. Okay, so at joint A, here's the pin, and we're going to treat each one of these members like they are they're just cables that can only apply forces along the length of the member. Okay, so at joint A, there's a reaction with the ground. I'll call that RA. And then there's a force produced by this member. I guess let's label this member 1 and this member 2. So there's what you can think of as a cable tension pulling on that pin from member 1. Okay. The only thing that's going to be different between this and a cable is these can also push. Cables can't push. So we're going to assume that there's this force pulling away from the pin that we'll call F1. And if we get a negative value, that just means it's pushing instead of pulling. Joint B at the top. What do we have acting on that pin? We have a downward force of 10,000. We have, since we're treating this like a cable, that pulling force is going to be the same one as that one. Yeah, so, and I'll just write it as F1 because I drew the arrow in the other direction. And then over here we have what I'll call F2. Yeah, we didn't use this truss simplification much in statics. Oh, yeah. We just used it for a day or two. So this isn't really the way we spend most of our time doing structures, but it's a fast way to do these problems. And then at joint C, we have the reaction at C, and then this force F2 pulling on the pin. And all we're trying to find is F1 and F2, which means that if we use Newton's second law for this pin, that gives us enough information to solve what we want. Where? So instead of isolating a member now, we're isolating a pin. And that pin has two forces acting on it. A force from member 1 and a force from member 2. But the special thing that we know, because this is a truss, is that all F1 does is pull or push along this line. And all the member 2 does is push or pull along this line. So we're using the fact that we know the directions of those forces instead of treating those as force vectors, and now we're just trying to find those scalar values, how much it's pushing or pulling. All right, so we'll go from this to Newton's second law. And Newton's second law says 0, negative 10,000. Plus F1 times a unit vector in that direction, which is negative 0.5, negative 0.866, plus F2 times a unit vector in that direction, positive 0.5, negative 0.866, is equal to zeros. And so we have two equations. The first one says negative 0.5 F1 plus 0.5 F2 is equal to 0. And the second equation says negative 0.866 F1 minus 0.866 F2 is equal to 10,000. So this is a really fast way to do problems where you can make that truss simplification. If you don't want to do it this way, you can do it the way we did it in statics. It's just, more equations, bigger system. It's not a big deal. It doesn't take much longer unless you have really huge numbers of elements. And so I'm going to do examples both ways, and you can choose which way you want to do. But can someone, let's see, do I have this solution? Can someone plug that into a calculator and give me the answer to this system? So we're going to get a value for F1 and a value for F2. All right. What does it mean that we got negative values? That's right. So since they're both negative, well, we assumed that it was in tension. And so if you get a negative value, it just means it's in that much compression. Okay. So both are in compression. And so the stress for well, let me not skip so many steps. So member 1, let's think about that one. Since we had a negative value, that means it's loaded like this. And I'll put the x-axis along the long axis of the beam. And so the XX stress is equal to negative 5773 divided by the cross-sectional area, which was 5 times 10 to the minus 4. This is newtons. This is meters squared. And can someone divide that? Okay. And it's negative, which makes sense that this member, the stress values would be in tension. Yeah, you're right, in compression, right. Everything else is, so if you think of this as a stress cube, it's loaded like this. (1.15 times 10 to the 7). And so the stress tensor is negative 1.15 times 10 to the 7, zeros everywhere else. Nope, nothing else. So now we're back to the topic here, which is we're only dealing with elements that are loaded according to the rules of stress tensors, you know, the rules of like stress elements. So if you have something like this with only fractions going, you know, inward along the x-axis, then this is the corresponding stress cube. Now, a stress represents a single point on a body. So what points does this represent? It represents everything in the whole body. That's like sort of the beauty of this thing, all of these kind of problems on bodies that follow the rules of stress cubes. The only place that you can't trust those results is at the end. So St. Venant's principle says this is the stress tensor that represents any point you choose in the white area. It just doesn't represent the red areas. And then if you wanted to find the strain, you use the compliance matrix, just like we were doing before. If you wanted to find the principal stresses, well, this is the principal stress tensor because we didn't have any shears. But if you wanted to find the maximum shear, you'd take 0 minus negative 1.5 times 10 to the 7 divided by 2. That gives you the maximum shear. So all of the stuff that we did before this still works. Yep. Yeah, first you find the forces, then you divide by the cross-sectional area, and then make the stress tensor out of that. Yep, and I think the assignment problems will all pretty much ask you to give the principal stresses, give the maximum shear stress, give the strain, all that kind of stuff. You'll keep being asked to do that. Okay, that's all.